Okay, this section 16.8, relative motion analysis using rotating axis. The last section of this chapter 16 deals with problems where there is sliding between moving bodies, and the motion of a point of interest B is described relative to a reference frame that is rotating with angular velocity omega and angular acceleration omega dot, rather than being a translating frame like we saw previously. So we have the fixed frame, capital letter XY, and then the base point A, and the moving frame, lowercase x, origin at capital A at A, and Y is also it's translating. The origin translates and rotates, and the point B is changing location in this moving frame. So we have the XB and YB, or XB, YB coordinates of point B are a function of time. We're going to assign unit vectors, capital IJ to the fixed frame and lowercase ij to the moving frame, to xi for x, lowercase j for y, and position problem is similar to what we saw before, with the difference that the relative vector of B with respect to A is changing in both magnitude and orientation because of omega. Okay, so RB with respect to a vector has these two components relative to the moving frame, lowercase x, A, and Y. The velocity problem is one of calculating we tackle it by taking the time derivative of the position equation from before. So the absolute velocity of point B is going to be absolute velocity of point A plus the time derivative of this relative vector of B with respect to A. Now this vector is changing both magnitude and orientation, and because of this, of the A, I, and J components, unit vectors rather, they are functions of time. It's no longer translating frame. Applying chain rule to take care of this third term gives birth to the time derivatives of these unit vectors. Problem is not new to us. It's explained here in the text. We saw this when studying circular motion or curvilinear motion using tangential and normal components, and there we saw that the time derivative of unit vector ut, the unit vector associated with the tangent of the path, is so time derivative of that unit vector is going to be this is omega, time derivative of theta omega times the normal vector. And here in this chapter, we see the same thing. So time derivative I with respect to t is going to be omega times j, and time derivative of j with respect to t is negative omega times I. So we're going to make use of could be also written as cross products. we're going to make use of them to replace their or substitute them here respectively. After collecting terms and reorganizing the equation obtained from the calculated derivative, time derivative, we obtain this form for the velocity, absolute velocity of point B. I want to go back to the original figure and mention something that is not done in this book, but other books do it, and it helps with understanding concepts. So we have, or other books introduce a point P, which coincides momentarily with point P coincides momentarily with B, but it's fixed relative to the moving frame. So this velocity equation appears to have one additional term. This is relative velocity of point B with respect to A in the moving frame. So this first part, it's something that we saw before. It's the absolute velocity. So this would be velocity of that point P, absolute velocity of that point P. Equals velocity of the base point plus was omega. We had it omega crossed with R of B with respect to A. Okay, so we can say that velocity of B is velocity of the point that momentarily coincides with B, but it's fixed relative to the moving frame, plus there was a plus here, plus the relative velocity of point B with respect to A measured in the moving frame. Okay, so the author calls this term angular velocity effect caused by a rotation of XYZ frame. Again, the use of that momentarily coincident point P helps a little bit with understanding concepts. Because if we have no relative motion of B in the moving frame, then this becomes zero, and we're going back to the relative velocity using translating axis. For acceleration, we need to take the time derivative of the velocity equation, and this is explained here. So we're going to apply chain rule because omega is function of time, R of B with respect to A is function of time. So after, and likewise we're going to see time derivative of unit vectors lowercase I and lowercase j. So after rearranging and with using the same previous result, we're going to obtain an equation that is somehow familiar to us. So if you look at just these, will be 1, 2, and 3 terms. This would be the acceleration, absolute acceleration of that point P, which momentarily coincides with point B. Okay, but it does not move in the relative to the moving frame. So absolute acceleration of B is absolute acceleration of A, and this would be the tangential velocity of point P relative to A, and this is going to be the normal acceleration of the momentarily fixed point P relative to A. This term, this last term, is the relative acceleration of point B with respect to A in the moving frame. Okay, so so this is one, and then we have the 2 omega crossed with relative velocity of v with respect to A in the moving frame, and this one, it's called Coriolis acceleration. Okay, so this Coriolis acceleration, which is a new concept, is going to be, if you look at again, being a cross product, omega has the direction of z. So if you cross omega with the relative velocity, you get a vector that's perpendicular to the velocity vector. And whether omega is positive or negative, that will be in one direction or mirror relative to the velocity vector. The book explains that Coriolis acceleration identified first by this Frenchman Gaspar Coriolis is of significance when you have say missiles moving in the gravitational field, and they occur because of the Earth rotation. So if you're on the North Pole looking south, you're going to see the Earth moving to your right. I'm sorry, to your left. So the direction of omega would be towards the north or polar star, north star. So a missile that is launched south from the North Pole, so velocity goes down south, and with omega perpendicular to it, so we're going to see an acceleration that is going to be to the left. So the missile will have a tendency to drift to the left, to east, drift east. And there's the book does not mention this. It's called Baire-Babinet law, which tries to explain, using Coriolis acceleration, why rivers flowing in the northern hemisphere erode their right bank more than the left bank. Okay, so Mississippi River, according to this theory or law, would erode more the west bank and would have a tendency to be curved to the east. Okay, so this was one, and I guess the theory from the chapter would be about this. So again, just the first three terms are something that we saw before. This would be the absolute acceleration of a point that coincides with B but does not move. And if the point moves, if we have velocity and acceleration, and yeah, acceleration might be zero, velocity could be constant. We still have the Coriolis term, but the point could also, like a constantly flying missile or constantly flowing river, water on a river. But if it's also accelerating, then we have this relative acceleration term, and then the Coriolis term is just, if we have velocity and we have rotation, we have Coriolis acceleration. Okay, so it's a procedure of analysis that explains is consideration in terms of choosing the reference, the moving frame, and then application of the two equations. Sometimes it becomes convenient to express these two vectors, or maybe acceleration vector in particular, are fully relative to the moving frame. Okay, rather than so you can either perform these analysis in the fixed frame or in the moving frame. You can the magnitude of the vector will be the same, and then you can do one last change of reference frames to, if you're interested in the x and y components relative to the capital X and capital Y frame. Okay. This is actually the case of this problem here, sample problem 1618, where we have a rotating collar. It rotates clockwise, so this would be the omega, capital omega, and this is capital omega dot. Okay, and it's moving outwards. We're given a position 60 degrees where we need to perform the analysis for this position. Of course, these are not position dependent, so you could easily draw the rod horizontal and have lowercase x-axis coincides with uppercase x, and y-axis coincide. Anyway, so the equations that we saw earlier, in order to implement them, so what would be we have point C, it's from the equation is point B. We have point O, that was the equivalent of A, and these two have zero velocity and acceleration. O, it's a fixed point. And then, of course, the velocity of C with respect to O, it's the one that's given, 2 meters per second, and has only a lowercase I component. And then the acceleration likewise has an I component only, and it's just a matter of evaluating these cross products. The omega crossed with omega, we know this is omega squared, so it's going to be negative omega squared times the position vector, like we saw it in the earlier in relative motion analysis, translating frames. Okay. Another sample problem, this one 1619, shows a collar that is pinned relative to link AB. The motion of link AB is given. We know its angular velocity and its angular acceleration, also the angle here, 45 degrees. And we want to find the angular velocity and angular acceleration of rod DE. Okay, so the equations to use are those that were introduced in the chapter or in the section where we express the velocity of C and describe the absolute velocity of C was tools provided with respect to the motion of rod D that we need the angular velocity and acceleration, angular acceleration found. Okay, so point C is a point B, point D would be a point A in the way the equations were introduced. The reference frames, lowercase, uppercase x, y, coincide, and it's systematic to put everything in a table. So we have D as a fixed point, so the velocity of D is 0, as well as acceleration, and intuitively omega and alpha are clockwise. If they are, then the omega and omega dot would be negative. Omega D and alpha D times K unit vector. Motion of C with respect to the moving frame. We know the position vector, but we don't know the relative velocity and relative acceleration fully. We know just that the two are along the x-axis. Okay, so with this information, that equation 1 and 2 before they simplify to these forms, and so let's see, we have velocity of C with respect to D, and okay, so in addition, what we need to do is to add information about the motion of point C with respect to the moving the input link AB. Okay, so velocity of this is the second set of equations. So velocity of C is velocity of A plus velocity of C with respect to A. Velocity of A is 0. The velocity of C with respect to A is omega of AB times R of C with respect to A, that is times vector AC. Okay, and then acceleration of C, it's acceleration of A, which is 0, and then we have the tangential component and the normal component of the acceleration. Okay, so this is useful because we add information in this part of the what will go into equations 1 and 2 on this part. Okay, so the with the new information, the equations 1 and 2 become, as you can see here, and we have two in terms of scalar equations, we have two scalar equations with the two unknowns, omega D and alpha of D, and by equating the I and J, or collecting the I and J terms, we're able to find the two unknowns. So I guess I'll stop here. 25 minutes of recording. We'll do additional problems in class.